Hello guys, welcome again to my YouTube channel, and in this video we're going to discuss about the turning effect of force. I know we all know what force is. So we always say that force is either a pull or a push. And the effect of force are: 1. Force can be able to move objects, and 2. Force can also be able to turn objects at a point. So these two properties about force is what we're going to discuss about in this topic, the turning effect of force. I can just give you a demonstration or an example of what we're talking about here. So now let us say, for example, you have a system like this, and then this part here is the fulcrum or the moving part of this system. So if you push it, what will happen is that this door will follow a path, and this path will be exactly like this. So it's supposed to go exactly like this. So my drawing is not accurate, but I know you get the point. So if you push this door, it is supposed to move in this direction like this. Now let us say, for example, we have 3 people. One of the person pushes this door from this point. So this person applies, let's say, force 1, and then we have another person here who pushes this door from this point. So let us call him F2. And then also we have another person at this point pushing the door. Let's say this one is F3. Now I want you to take note that in this example, these people are pushing this door at different times. Who do you think will use a lot of energy to open this door? So we always say that this person here, the F3 one, will use more energy to open this door than F2 or F1. F2 also will use a lot of energy to open this door than F1. F1 is the one who will use the least amount of force to open this door. Now you'll notice that the difference between these 3 is the distance here. So this one, the distance from him to this moving part is this. And this F2, the distance of him to this moving part is this. And this F3, his distance to the moving part of the door is this. So you'll realize that the more the distance, the less the force will be required. Because this guy here, his distance is this, and this guy here, his distance is this. This one uses more energy because the distance from him to the moving part of the door is very much little. It's very little. But this guy here, his distance from the point where he pushes the door to the point where this door moves is very long. So distance matters a lot. Now I want to give you another example. So let us say, for example, you have a swing at this point. So this is a swing. So at this point here is the fulcrum. Let's say it's exactly at the middle of this swing. And then let's say we have 2 different people sitting on this swing. So this person A, so let us say this side is person A. So this person A is thicker, is a little bigger. Let us draw him a little bigger. He's sitting at this point. So this person A is a little bit bigger. And this person B here, so this one is person B here, is a little bit smaller than this guy here. And remember, the distance between this guy and this guy is equal from the center point. So this distance and this distance is equal. So what do you think will happen in this case? So what will happen is that this guy here will apply more force downwards. So this swing will swing in the anti-clockwise direction, meaning this swing will move in this direction because this guy is more heavier than this guy and the distance is very small. So what do you think should happen in this case? So these people have 2 options. So one is either this guy should move in this direction or this guy should move this direction. Now let us consider the scenario 2 whereby this guy needs to move this direction. Remember, when he was sitting here, their distance was the same. But when he moves to, let's say, a point like this, you'll realize that this swing will now balance. So what do you think has happened here? What has happened is that we have varied the distance from this person to the center point. So distance matters a lot when it comes to balancing this system. Now, what is another thing that we can do to balance this system? Another option you have is you can move this person in this direction. So let us keep this person originally where he is and then move this person here. So we realize that we have reduced the perpendicular distance from this guy here to the center point. Hence, we'll be reducing the force acting on this part. So meaning the system will be in equilibrium. It will be balancing. Another thing you can do is you can take another weight and add on to this person here. So if you add another weight and let's say that weight balances, then this thing will balance. So from this examples, you realize that what matters a lot in this case is one, the force. So force, mostly we are talking about the weights. And two, what matters a lot is the distance. So let's refer to it as the perpendicular distance. These two things are very important when it comes to balancing this system here. Now let us look at moment of force. So what do you understand by moment of force? How can we define this thing? So we always say that moment of force is the product of force and the perpendicular distance between the point of support and the line of action of the force. So this is the product of force and the perpendicular distance. So this thing you need to take note of it. You said the perpendicular distance. What perpendicular distance? This perpendicular distance is between the point of support and the line of action. The point of support and the line of action. So that is the perpendicular distance you're talking about. So one thing that you need to take note of is one, we're talking about the line of action, and two, we have the perpendicular distance between the point. So these two things here are very important to take note of. One is the line of action of force, and two is the perpendicular distance between the point. If you master this, then no question will bother you when it comes to finding the moments of force. So let us give an example here. Let us say, for example, you have, let's say this is a door. Let us draw a door like this. So this is the fulcrum of the door. And then let's say, let us just draw a virtual line at this point, in the middle of this door like this. And then let's say you apply force on this door. We apply a force on this door from this point here. So applying force at this point. So this, let us call it as F. Let us call it as F1. So let us say we apply a force at this part here, and we know this distance. For us to find the moment of this force here, we need to take this force and multiply it to the perpendicular distance between the point. Now take note of this. We say that it is perpendicular distance and the line of action of force. So where is the line of action of force? So if this is the force acting like this, then the line of action is acting upwards. Another thing, perpendicular distance between the points. So what point are we talking about? We're basically talking about this point. So if we stretch this line like this, then where they meet, these two lines, they're supposed to be perpendicular to each other. The perpendicular means that it needs to make a 90 degrees angle with each other. If it makes a 90 degrees with each other, that's when you can say that moment of force will be equal to this force here. We call it F1. And then let's say the distance from this part here to this force here is, let's say, D1. So you can say it's equals to F1 multiplied by D1. And this is how we find moment of force, given that this force is perpendicular to this line here. Now, what if it is not perpendicular? What do you think is going to happen? So we can draw an example of such a scenario. And then this is the moving part. This is the moving part of this object. So let us say we have a force acting at this point here, but it is not perpendicular. It is at an angle like this. Let's call this angle here as theta. Let's call this distance here from this part to this part here where the force is acting at, we call it as D2. And then this force here as F2. how do you think we can find the moment of force given that this force is not perpendicular to this surface? So remember, this line here is not perpendicular to this line of force. So because if we stretch this, let us stretch this line from this point. If we stretch it and then we stretch the line of action force like this, you realize that this line and this one, they are not perpendicular to each other. They are not forming 90 degrees with each other. So that means that we cannot use this one as the perpendicular distance. So what we need to do is to find the perpendicular distance of this force 2, this F2. Remember we said that the moment of force is the product of force and perpendicular distance between the point of support and the line of action of the force. Mark these words, the point of support is this point here, because this is the moving part of this door. And the line of action of force is this thing here. So if you extend this line and this one, and you find out that this distance is not forming a 90 degrees, then that means that this is not the perpendicular distance. So for us to find the perpendicular distance, we will have to find a point on this line of action of force, this line of action of force that will form 90 degrees with this part here. So we need to find this part. So we can just extend like this, and then when you find that point, we draw a line like this. So we can extend this line going up like that, and then we assume this one is 90 degrees. So you don't have to like measure it, you can just calculate it. I'll show you how we do it. So this one becomes 90 degrees. Now we have made sure that this force is now acting perpendicular with this distance. So this is the perpendicular distance. So you can call it as capital D2. Now if you look closely, this angle here, remember this line and this angle is the same as this one here. Okay, it's just that we have extended this one down. So this theta here, we can also put it at this point. And remember, these angles are opposite to each other. So this part here will be theta. Okay, so this is a 90 degrees angle triangle. So let us draw a 90 degrees angled triangle at this point like this. Now you realize that this pointer here of the 90 degrees, where it points, always represents the hypotenuse. So the distance between this point and this point, this is the hypotenuse of the triangle. Because if you draw a right angled triangle, you realize that this sharp point here always points at the hypotenuse. So this is D2. So this D2 will be here. So this part here is D2. And then this so we can name this one as, let's say, D1. Let's name this part D1, the distance from this point to this point here. Let us name it as D1. But remember, we are looking for D2. This is the distance that we are looking for, because this is the perpendicular distance acted by this force here. Now, how can we be able to calculate this perpendicular distance, this D2 here? So remember, this angle said it is theta, so meaning this part is theta, and this part here is also theta. So this part here is also, we can just label it as theta. Now we can use the SOHCAHTOA. So which one do you think we should use? Because when you're given this question, you'll always be given D2. So you have D2 and you have this angle here, because you'll be given this angle acted by this force and be given D2. So we will have, so D2 is the hypotenuse and this is the angle. And remember, we are looking for the opposite, because this angle here, this one, we are looking for this opposite here. So we have the hypotenuse and we are trying to find the opposite. So we can use sine option, because we have theta and we have the hypotenuse. The hypotenuse is this one, this D2, and so we are finding the opposite, which is this perpendicular distance. So you can write it as sine theta. So theta is this angle, it will be equal to opposite all over the hypotenuse. And what is hypotenuse? The hypotenuse here, this one is the small d2, this distance here. This is the perpendicular distance we are looking for. So for you to find d2, so d2 will be equal to, if we make this the subject of the formula, it will be d2 sine theta. And this is how we find the perpendicular distance given that force is acting at an angle. You just take d2 and then you take the sine of the angle. Another thing you need to take note of is which angle you are given. If you are given this angle here, if this is the angle you are given from this part to this part, let me change the color. If this is the angle you are given from this part to this part, then we are supposed to less 180 because this is the angle we want and not this one. So make sure you always take note of which angle you are given. This is the angle that we want and not this one on this side. So let us say, for example, you're given a question like this, whereby you are told to find the moment of this force here. Now, take note that this line of action of force, this line of action of force is going in the upward direction. And this moving point, so this is the moving point. If you follow this line, you realize that this line and this line, they are perpendicular to each other. They form 90 degrees, meaning this distance here is the perpendicular distance that we want. So this one is easy. We always say that moment of force is always equal to the force to multiply by the perpendicular distance. So here we will take the force we are given, which is 5 newtons. So we'll take 5 and then you multiply by the perpendicular distance, which is 10 meters. So you'll take 5 multiplied by 10 and you'll get your answer as 50. Remember this one's here, this unit is in Newton and this unit is in meters. So the SI unit will be Newton meter because you are multiplying these two. And this is the answer to this question. So let us do another example on this. Now let us say, for example, you are given a question like this, whereby you are told that this 5 newtons is acting on this. Let's say this one is the moving part, this is the moving part of the door. So this 5 newtons is acting with this angle of 60 degrees, and this is the distance from this point to the point where this door moves. So how can you be able to calculate the moment of force given this question here? Now let us follow the path of this movement of force. So let us follow this path. So this is the line of action of force. This one here is the distance from the point of support. Now I want you to take note that this one here is not 90 degrees. So this 10 meters is not the perpendicular distance because it does not form 90 degrees with the line of action of force. So we need to find the 90 degrees point. So what we normally do is we elongate this line going up like this, and then when we elongate it, we connect this part to this part here. So this will be the perpendicular distance. So this distance is what we are looking for. Now we always assume that this part is the 90 degrees mark. So this line and this line should make 90 degrees. So this is the perpendicular distance because it will make 90 degrees with the line of action of force. Now remember, this is 60 here. So this one also will be 60 because they are directly opposite to each other. Now if you draw this triangle, let us draw this triangle. Now the hypotenuse is this one because you said this arrow always points at the hypotenuse. The 90 degree mark always points at the hypotenuse. So this is the hypotenuse. So the distance from this point to this point is exactly 10 meters. So this is 60 degrees. And you're trying to find the opposite. And we said we always use the sine. So we always say that sine, so let us call this one as x. So let's sine is equals to, so sine theta is equals to opposite is x all over the hypotenuse, which is 10. So if you calculate this, you'll get that the distance, this x, so this is the distance you're talking about. So x is equal to 10. So we take this 10 and multiply both sides by 10 and here by 10. So it will be 10 sine theta. And when you calculate this one, you'll get the perpendicular distance. So this is the distance. And always say that moment of force is always given by the force times the perpendicular distance. So we'll take force multiplied by the perpendicular distance. So the answer will be, so we will take 5 newtons multiplied by the distance, which is 10 sine of theta, and your total answer will be approximately 43.3 Newton meter, and this is your answer. So this is the trick. This is the trick of finding the perpendicular distance given that your force acts at an angle. So if the angle was 30, so you'll only replace the theta mark. If your angle was 10, then you put the 10 here. If your angle was 5, then you put the 5 here. So this is the trick of this question. So you just need to know how to apply this formula to find the perpendicular distance if your force is acting at an angle. So you can pause the video and try this question and then leave your answer in the comment section below so we can get if you have understood this topic or this section or not.